everyone. So we are going to have our lecture 17, EE341, microelectronics. We didn't have lecture last time because we just have midterm, and midterm was in a joint slot. So that's why that is a compensation for the lecture. So what we are going to do today, we will start a new topic, and that is feedback. And it's chapter 12 of your book, Fundamental of Microelectronics by Razavi. So we will start a new topic. So in general, we will talk today about the feedback, and then we will also apply some small concepts on the circuits which we have seen, but mainly more in the next lecture. But today we will more like make a sense why we need a feedback system. In parallel, you are also taking a course on feedback and control system. So might be today's information will be a refresher or just like a very much basic what you are already covering. So the first and the most important thing is feedback and why we need a feedback. So feedback, and especially why we need the feedback in the analog circuits, feedback systems. So if I want to ask about feedback system, so in your opinion, what a feedback system do? Why we need a feedback system, for example? Why we need a feedback system? Feedback system. So if you can recall from your course for feedback or in genetic, we can see that, okay, you are, for example, there's a person named as X. Okay? So the X person is driving a car. He is driving a car. This X person is sitting here and driving the car. So the X person is driving the car. What he is doing, he is initially got his license at the age of 18 years, and his parents told that, okay, you need to drive at the speed of 40 miles per hour, or 40, let's say in Pakistan, we have 40 kilometers per hour, okay? And he adhered to that policy that, okay, he was following that the speed should be 40 kilometers per hour. But as he starts seeing the things, he starts seeing that, okay, his surroundings are overspeeding. They are going to 60 kilometers per hour or 80 kilometers per hour. So when he analyzed this behavior, he starts increasing. So he goes to 60, he goes to 80, he forget what his parents told because he has to cope up with the society. And then sometimes he starts increasing to 100 on those roads which was not allowed. So one day what happened, he was going to on the same speed and he got a challan or a ticket. Why he got a challan or a ticket? Because he was doing overspeeding. And when he got a challan or a ticket, he got to know there was something wrong he was doing. And what was that challan or ticket? That was basically a feedback which he got, and he ultimately tuned back to the normal speed which he was driving, 40 to let's say 80 kilometers per hour. And now after this lesson, after this feedback system, he got to know that the speed should be in a certain range. Okay, so that's basically the overall generic depiction about a feedback system. Now we want to integrate this feedback system in a overall, like the components in this overall application. So if I want to derive a feedback system, I would say something that we have some in a feedback system, a feed forward path. Okay, so we have a feed forward path which doesn't need ultimately any negative feedback, in a sense that when he was speeding the car, he was driving the car, pressing the accelerator, that was a feed forward system for the person X. Okay, so the person X was doing an input, he was applying, accelerating, that he doesn't need any sort of feedback, and he was going fine. But what happened, somebody was measuring his speed. So the police, how they measure the speed, why is the speed, how they measure the speed, with the help of radar, with the help of some speedometers. So they were measuring the speed, and when they measured the speed, they were measuring it. So the police was measuring the speed or sensing the speed. Okay, so they were sensing with some instruments. So that's basically some sort of measurement or sense that speed. So one instrument comes, we need to sense that speed, and once we sense that speed, we need to give some feedback. What sort of feedback was given here? The feedback in this case was given a ticket, a money he has to pay, because, or he has some negative points because he was over speeding. So first thing is a feed forward, that you are accelerating. Second thing, you need to measure the output, that's the sensing, and then there should be some feedback mechanism, meaning that there should be some ticket, some negative impact has to be done, and what ultimately result, the speed has to go down. That from that feedback mechanism, he got to know he has to deaccelerate. So negative feedback has to be given, or action has to be done. In this case, in Ahmed case, or in X case, he did the action on his own, because if he don't do action on his own, he will again get ticket, and multiple tickets will lead to cancellation of his driving license. So that's the common feedback system which we have in our system, which do what? Philosophically, what it controls us, bring us in our limits. That what are our limits? Okay, stabilize us, make the system stable, because increasing the speed more and more can be dangerous. So it makes us stable, it controls the environment, it limits. So now we are going to bring the same analogy towards the amplifier, why it helps there. But before moving forward, let's derive the relation, that what is the what we are losing from a feedback system and what we are gaining from a feedback system in terms of quantitative relationship. So moving forward, we have an input X. So let me write with a different color. We have an input X. Hopefully today's lecture will not be difficult, because it's just a revision for your feedback concepts. But I want you, all of you, to review the things, because once we are going to apply the circuits, we want to a little bit more sharper. So we have an input X, we have an output Y, we have a feed forward gain, we will call feed forward gain. I'm not giving the same example of your throttle and those things, but that's going to be more specific. But you can apply any example. I just give more like a generic example, and a feedback gain. Feedback. And this system is a negative feedback. Most of our systems are negative feedback systems. We also have some positive feedback systems, but they are rare. For example, we can have a feedback system as an oscillator. When we generate a clock, basically, we want to oscillate. So this is a positive feedback system. And also the latch. The way we store the data is a positive feedback. A digital data we store, that's a latch, basically. So that we want to retain the value, the way the data is stored in the memory. That's also positive feedback system. We are retaining the value, okay? So both of these are examples of a positive feedback system. You can think more around you. But in the electronics, I'm giving you one on the analog side, which is an oscillator. Also in the digital, we have a ring oscillator, which is a digital system, but it's a positive feedback system. Similarly, a latch, a digital latch, the way your memory is being governed, or memory, you are storing the data. So let's coming back. In this system, we have an input, which is X, output, which is Y. we have a feed forward path A, and we have a gain of value K, right? So if we just want to derive the system, I can write my output Y is equal to something which is here. Let's write the name XF, for example, anything is XF times A naught. Okay. We have A which is being multiplied. We have an Y which is being multiplied, a multiplication of XF, the signal at this point, times the feed forward gain A naught. And what is XF? XF is, if I want to write this Y as XA, I'm just writing the names, might be they're not relating with the book, but I'm just writing. So XF is what? X minus XA. And what is XA? XA is Y times K, or K times Y, whatever the way you want to write. So we have these three things. And if we just combine all of these three things, we will have Y is equal to X minus YK times A naught. And if we further do manipulation, we will get Y is equal to plus A naught YK times X. And we want to have Y is equal to 1 plus A naught K times X. And we can write it that Y over X, which is output and input relation, is equal to, yeah, so there was A naught also coming here. A naught coming here. So is equal to A naught divided by 1 plus A naught K. And that is a pretty much, you are familiar with the feedback gain or a closed loop. This is closed loop gain formula. So ultimately what happened, your gain is being reduced by 1 plus A naught K times, where A naught is the feed forward gain and K is a feedback gain. So your closed loop gain in a feedback system reduces. So one thing we got to know, we are getting less gain as compared to a feed forward path, but we will see what are the benefits we are getting here. The benefits are basically here. We get more control, we get more limit, we get more stable. And one thing which I want to elaborate, that because of this feedback system, let me write the equation again. Y by X is equal to A naught 1 plus K times K naught. So as we said, A naught is a feed forward gain, which was the initial gain, or we normally call it open loop gain. Open loop gain, right? So there's an open loop gain. Y over X now is a closed loop gain. Right? So, and if, for example, Ka naught is pretty much bigger than 1, what's happening? Y over X will be approximately equal to A naught divided by K times A naught, which will be equal to 1 over K. And that's something very much interesting, that if K, the product of feedback gain and the feed forward gain, is bigger than 1, pretty much bigger than 1, my closed loop gain becomes 1 over K. And that's 1 over K is what? Inverse of feedback gain. So that's like we have something which is limiting us, that A naught, which was initial gain of the system, set aside, and we are governed by some another factor K, which is somehow ruling us. Before moving forward, I would like to bring this to an amplifier so that we can see the benefit which we get. But for the first and the most important thing is that now our gain is not dependent on A naught, rather it's dependent on another factor, which is a feedback, or feedback, like a one inverse of feedback gain. So, and that is K. So let's apply this to our amplifier analogy so that we can link the things and we can talk more about the benefits which we are getting from there. So let me draw a simple circuit so we can link the things. So this is a gain, just the same gain which we have drawn. Let me write the gain as A naught. Here we have plus, here we have minus, here I am applying my input X, the same thing. And here there's a feedback path. Feedback path, this is my output, Y. So now you can see this is an amplifier for us. Amplifier have an open loop gain, which we all previously deriving, GMRO, GMRD, whatever the gain we were having, is A naught. And we have a feedback path, which is coming here, which is a negative feedback. Since going to an inverting terminal, it's a negative feedback, and that is somehow written here. Now, if I want to find out, one way is we can directly write the expression. We know that Y over X is equal to A naught divided by 1 plus K times A naught. And K is equal to something which we want to figure it out. So K will be ultimately equal to, I will derive it for you, to R1 plus R2. But if you want to derive the relation, we can just figure it out. We have this again, let's give this name, this terminal known as XF again. So Y is equal to X, it's an amplifier, so differential amplifier X minus XF times A naught. Okay, यही हो जाएगा. And what is XF for us? XF is equal to, is a voltage division, so it's going to be R2 divided by R1 plus R2 times Y. Okay, and if we plug in 1, we will be Y is on the left, we will be left with some expression which will be equivalent to A naught divided by 1 plus R2 divided by R1 plus R2 times A naught. So this is the same expression which we have designed for the generic system, and now we are deriving the same thing for an amplifier. So it tells us some important aspect. The important aspect is that if, for example, R2 divided by R1 plus R2, A naught is pretty much bigger than 1, what's going to happen? My Y by X is approximately equal to, it's basically, let me just elaborate it. It's will be equal to R1 plus R2 divided by R2. So it will be somehow in this fashion. It will be equal to 1 over K. And that's telling us something, that previously my gain in an open loop configuration was equivalent to K naught. But now, if I'm talking about the gain in an open loop configuration, for the open loop, it was equivalent to this thing. But in a closed loop, if my A times the K is bigger, my gain is equal to something like this, 1 plus R1 over R2. This is a closed loop gain. Okay. Which one is better? Let's talk about these things. In an open loop gain, let me draw a simple amplifier, what we are meaning. We have this GM, we have this RD. So my gain A naught was equal to, just ignore the sign, it was GM RD. But now I am saying my gain is not dependent on this GM RD, rather my gain is dependent on something like this. R1, R2. So it's depending upon the ratio of this R1 and R2, and this is my V out. Okay. So, and that's pretty much interesting. Why my gain is now becoming something like this configuration. Now let's talk about A naught first. What is about this A naught? What are the issues with this A naught? Because before seeing the benefit of the feedback, we need to see the issues in the open loop gain. Do we have any issues? If we have any issues, yes, we need to find an alternate. If we don't have an issue, we don't have to look for an alternate. So issues in open loop or A naught. That's why I write the GMRD. So the GMRD, the biggest issue in the GMRD is PVT variations. What is meant by PVT variations? You design a gain for a 10, for example. You want the GMRD to be 10. Okay, well and good. But what happens because of this variation in this process voltage and temperature, your RD varies, your GM varies. And because of this variation, the gain might be 9, the gain might be 11, the gain can be 10, 12. So it will not be 10, which you are intending for. And the runtime, it might change. And that's hurting you. And top of it, RD. What happens with the RD? It's a load resistance which can change. It's basically load which is being seen by this amplifier. This is RD can vary also on the runtime. So because of that variation, also the gain changes. What about other things? Frequency. We all know, we have seen this sort of patterns, that as the frequency increases, the gain also reduces. So if I want to see here, my gain is bigger, 10, for example. What about here? My gain is less. So my system becomes frequency dependent, and that I'm losing if I use A naught. I'm not getting all the time same gain which I'm intending for. And that's the biggest drawback for the open loop configuration if I talk in terms of amplifiers, if I talk in terms of analog circuits. What about this closed loop gain? Is it solving my issue? Let's see this thing. Now the closed loop gain we saw, if we have an A naught, which is a pretty much bigger, or product of A naught times this case pretty much bigger, my gain is 1 plus R1 and R2. How it's solving this PVT variations? Now, if the PVT variation mean that because of process variation, they are going to some variation in this resistance, which should be 1 kilo ohm, it's not 1 kilo ohm, rather it's 1.2 kilo ohm now. If something is affecting this resistor, if this is of same material, this is also going to be affected, 1.2 kilo ohm. The net gain closed loop will remain same. If previously it was 10, it was again 10 if I increase both of them. So we are not losing anything if they are of the same material. So here it helps me. Same thing. Now there is no voltage variation which is affecting, or there is nothing which is affecting the bandwidth, only the resistance R1 and R2. So any variation which is happening R1 will happen the same variation in R2. So I'm on the benefit side. So this is the one of the biggest benefit I get in terms of closed loop gain, that my system becomes prone to PVT variations, and I can have a fixed control over the gain, which is required in all the system, fixed control. Why the fixed control is required? If you see what happens if I want an amplifier designed for a gain of 100 and it's giving me 120. What's the difference? You can see in the speaker. If you have a if you have a speaker and you set the gain for 100 and in between runtime the speaker goes to 120, what will happen? It will be a very much loud voice. Nobody will be able to hear. For example, if I start screaming, it will be similar to that thing. We don't want those things. We want explicitly a closed loop system, which should be a realistic, having a fixed gain for which I designed for. I don't want runtime variations. So that's one of the main things which we need to understand. Let's do a small example before we move forward. Or we need to express, still we didn't express one expression. Then let's do that expression and then we can do one example. So the expression is for the error. Again, you have definitely done this expression. Let me draw the circuit again. So we have this system, we have a feed forward path going to feed forward gain, going to an output. Output is going back to the feedback gain and going as a negative feedback. Okay? So we talked about this difference which is coming here, and I previously mentioned is XF. Let's give a good name to it. And because this is somehow error, so I can give it E. And let's give this name as an error. So E, if I wanted error function, is equal to X minus XF. So if I want to write E, my E is something like this, and XF is equal to xf will be equal to this times a naught. So it will be y times k, which is equal to e a naught times k. So I can write x minus e a naught k, which is equivalent to, it will go on this side. So x or e I can write is equal to x divided by 1 plus k times a naught. What it is telling us, error is the difference between the feedback path and the feed forward signal, or the input signal, sorry. So if I want error to be 0 or near to 0, I want k times a naught to be very much bigger quantity. So if k times a naught is a very much bigger quantity, my error will be almost 0. This means x is somehow equal to x is equal to xf. If x is equal to xf, this means that my signal is stable. Now there is no need at this moment, if we want to take example of the X person who was driving, that now he's driving properly under the speed limit and there is no need for him to get a ticket. So that's very much important thing. So that's why we want all the time this thing which is k times a naught to be very much bigger than 1, or in general a naught should be very much bigger than 1, or open loop gain should be high, and that basically helps us in deducing the signals. Now what is this k times a naught? That's very much important. This k times a naught, which is used multiple times now in this error expression and also in this gain expression, a naught divided by 1 plus k a naught. This same k a naught is basically known as loop gain. So we need to be sure about these terminologies because they are going to be used again and again. So there is a terminology known as loop gain. Loop gain is what? It's product of feed forward gain and feedback gain. So it's not doing anything else. It's just a product of feedback gain and a feed forward gain. Now, what it do, it gives a lot benefit when we are going to later on discuss this thing. But at this moment, we just want to analyze what this infer us, or how we want to see this thing, what is the benefit it is telling us. So let's, for that simple analysis, just let's do a simple analysis of breaking the loop, because the feed or the loop gain is ultimately, whenever we are going to break the loop, we can figure it out how much the gain this loop is having. So let's break the loop, and at a certain point, for example, at this point, we will break the loop and we'll follow the same pattern, and we will apply a 0 input. X will be grounded, but we will apply some input at the node where we are breaking. So if we are breaking here, this will be input now, and we are observing the output at the same node. So let me redraw the things for you, so for better clarification. As I mentioned, the input is grounded, the old input. So we still have this signal which is coming here. We have here something a naught. Here we are observing still an output. So this output, let's call it again y for simplicity. And we broke the here input, and here let's say we have feedback gain, and we are still applying this negative thing here, negative. And this is k, sorry. And this is, we are applying, let's say, an input. For example, we can have a test input. We are just applying an input, so we can say. And we are interested in finding y by v test. That's this expression. If we want to find y by v test, we can, let me write the same place. If we want to find y by v test, so here what we are getting a signal, it will be, so let me give the names for easy understanding. Again, I'm calling this signal as xf, and I'm calling this signal as xa. And just again giving some names. So y I can write is something which is a naught times xa. Okay. And XA kya hai is basically different. This is 0 here, so 0 minus XF. And XF kya hai? This is V test times K. So I can write minus V test times K. And so Y, final Y will become then A naught times, this is minus V test by K. And what it is, our concern was Y over V test. That is equal to minus A naught K. So whenever I am breaking the loop anywhere at this moment, I am having something gain which is equivalent to the loop gain. The negative sign we will depict later. What this negative sign is ultimately telling us, that ultimately is negative feedback. That's why the negative sign is coming. But the loop gain is A naught K. We can break at any other point and we might observe the same thing, because this is the loop gain which we are all at the time going to see. So that's what I was saying. There's an example in your book. So let me do that example for you and try to find wherever we place wherever we break the loop gain will remain the same if we go in from one direction to another. So now in this example 12.3, let me draw the circuit again for easy visualization. This is A naught, this is here your output Y, K, and plus, sorry. So plus negative feedback X. So again, instead of breaking at this point, I make this as again grounded and I break the loop at this node. So if I'm breaking at this node, this means I'm giving an input here, we test here, and I'm observing the output at this node. Okay. I will clarify again so that you all are comfortable. So I will just draw this thing. This is my axis 0. So I am drawing my negative feedback path here and I'm taking my output. So we just gave the name and an output. Let's say we can give this time N, so node N. So I'm taking an output and I'm applying a test source VT at this point, going to A naught times Y, and here we have K, which is going towards the distance. So again, we are interested in finding this time N. So let me write N by VT. So that is our goal. We want to find the output divided by input. It should be the loop gain in this case. By analysis, we can say it should be again equal to minus K times A naught, but we can again see this thing. So N is equal to Y times K, right? So no, so it's not going to Y times K. It's going to be N is equal to 0 minus Y. Okay, so you can see N is equal to 0 minus YK. So N is equal to minus YK and Y is equal to A times V naught. So A times V naught K, which is equal to N by VT is equal to minus A naught K. This is again a loop gain. So we'll bring this loop gain a lot in future when we talk about the phase response, because that is very much important. It helps us to depict the circuit in a very much beautiful way. Now let's depict a little bit more about the some terminologies which we just mentioned regarding the gate, regarding the gain, open loop gain desensitization. So that's why what we normally call properties of negative feedback. I'm writing NFB, negative feedback system. So the main property of the negative feedback is gain desensitization. Gain desensitization. Your gain of a system is not sensitive to your environmental variables. It's not sensitive to the PVT. It's not sensitive to the variations which are happening around the environment. So let's put some numbers and we get an idea that how your gain is not being affected by those variations. So there's an example I would like to do to clarify this point. So then again, example 12.4. In this example, what is being said that, okay, we have the same amplifier, which we have a naught here, we have an X, we have R1, R2, we have Y here. So there's again a negative feedback which is being applied here. And we just mentioned that Y by X in this specific case will be A naught divided by 1 plus K times A naught. And where the K, we just figured it out, K was equal to R2 divided by R1 plus R2. Okay. So K हमारे पास ये value थी. अब the question is that we are having the nominal gain of 4. This means the K value is given, which is equal to 4. The nominal gain, the closed loop gain is given to find. And we have to determine the actual gain, meaning we have to find the actual gain in the closed loop. We have to find the actual gain, which is basically Y by X, if the A1 or A naught is equal to 1000. So we are giving this information. So first thing we need to find, and also we need to find the actual gain if my gain reduces by 5. So that's what the task is. If my A naught reduces because of any process variation, because of any resistance going, because of any effect, my A naught, the open loop gain reduces by half, how much it affects the actual gain of the system, where I'm setting the ratio of R1 and R2 with the help of K. So first thing we need to find what is my R1 by R2. So we know that R2 divided by R1 plus R2 is given as 4 to us. No, sorry. So there was some mistake. Yeah, there's some mistake. So the closed loop gain is given. This means 1 over K is given as 4. Okay, so that's something which we need to ensure. So that's what, if 1 over K is given to us, we need to mention that 1 over K is equal to R1 plus R2 by R2, which is equal to 1 plus R1 by R2. So this is equal to 4. This means R1 by R2 is equal to 3. Now we can plug it back in this equation that we want to find Y over X for A naught of 1000, and we are given 1 plus K is 4, so 1 over 4 times 1000. This is just confusing between these two. So 1 over K is this thing, so you can have it A naught divided by 4. So it's going to be 1000 divided by 1 plus 250 equal to 1000 divided by 251, which will be equal to 3.984. So the system gain is 3.984 if my open loop gain is 1000. Okay, and I designed for 4, so that's fine. If my K, if my A naught becomes 500, what will be the impact of this open loop reduction on the closed loop gain? Everything else remains the same, and I need to find the Y over X when my A naught becomes 500. The open loop gain, you need to identify, it becomes half. But what about the closed loop gain? So it becomes 500 divided by 1 plus 500 by 4 equal to 500 divided by 1 plus 125 equal to 500 by 126, which is equal to 3.968. So what it is telling us, that the gain reduces very much small. The closed loop gain is very much minutely touched, that it's almost the same. Even the open loop gain become half. So we conclude this thing, if my open loop gain is a very much big value, like a 500,000, it's not going to affect my closed loop gain. And that's the main benefit of a feedback system. That feedback system makes the system insensitive to the variations apart from the ratio of R1 and R2 in this specific case. So that makes your system robust against any process variations. Okay. As I mentioned, that it's not only because of the process variation, it can be because of the frequency, it can be because of this resistance variation, it can be because of any other concern based on which the open loop gain is being dependent. For the cascode, we already have seen a lot of things are there which can vary and which can change the open loop gain. So any variation which can change the open loop gain with a slight variation, actually, as far as it doesn't become a lower value, we can make our system still work because of this feedback path. Okay. Now let's bringing back to another strong notion regarding the bandwidth extension that is also related to the feedback. So another important thing is the bandwidth. If you remember the bandwidth which we have seen in the frequency response in chapter 11 for any amplifier, if we just assume a single pole, so we have an amplifier. Now we write in terms of frequency that, okay, we also have something frequency. So we have this DC gain divided by 1 plus S over omega naught. So this means we have a single pole DC gain of A naught at a frequency omega naught. We have a cutoff frequency, so minus 20 dB per decade. And a single pole, okay? Just for a easy हम लोग single pole system ले रहे हैं. So minus 3 dB bandwidth is omega naught. Now if I want to reflect back in the feedback system जो हम लोगों ने अभी देखा है, we will have something like this. Y over X will be equal to, now instead of A naught, I am having an A1S. So A1S divided by 1 plus, everything becomes frequency dependent. A1S. So let's write the things. It's going to be A naught divided by 1 plus S over omega naught divided by 1 plus K times A naught 1 plus S over omega naught, dividing and multiplying by 1 over S. 1 plus S naught will bring us A naught divided by 1 plus K times A naught plus S over omega naught. Again, taking things common, it will result into 1 A naught divided by 1 plus K times A naught, okay, divided by 1 plus, just I'm taking the things common, S divided by 1 plus K naught, A naught, K A naught, omega naught. So what we can see infer from this relation, just a little bit before moving forward, make sure just pause the video and see what this relation is telling. And just took this 1 plus K naught, K8 naught common from up and down, cancel it, and I come with this relation. What this thing is telling me basically. So that's something very much important, which we need to identify that, okay, that is something which we want to figure it out in our relation. This is the relation of a closed loop system, we can see. And this is something similar analogy to this one. This is for the open loop. Okay, open loop. So for the open loop, we have a gain A naught, and then we have 1 plus S over omega naught. That was telling us the frequency of the pole information. Same thing. Now we have this thing, A naught divided by 1 plus K over A naught as a closed loop. So this is a closed loop gain. Closed loop gain. Just make sure to pay specific attention. The closed loop gain is 1 plus K A naught. This might be different from your feedback course. So A naught divided by 1 plus K over A naught is your closed loop gain. Good job. And what about the bandwidth? This is your bandwidth. Previously, my bandwidth was omega naught. What is my bandwidth now? Closed loop bandwidth. Let me write BW for the bandwidth. Now my bandwidth is equal to 1 plus K times A naught omega naught. My bandwidth previously was omega naught. Now the bandwidth is 1 plus k times a naught. So bandwidth has increased, whereas gain has decreased. And by what amount? The same amount by which my gain has been reduced, 1 plus k a naught, or loop gain, the same amount the bandwidth has increased. So that's why we normally called in analog design for an amplifier, the gain bandwidth product remains constant. I cannot gain everything. I increase the gain, my bandwidth will reduce. I increase my bandwidth, my gain will reduce. And that's pretty much what this expression is telling us. So that's why we also need gain insensitivity because of negative feedback, bandwidth extension because of negative feedback. That's very much important. We increase the gain, we reduce the bandwidth. We reduce the bandwidth, we increase the gain. And overall, the gain bandwidth will remain constant. Let's see this small point with the help of an example also. If, for example, it's an example 12.5. So what we are given, K, the feedback gain is equal to 0.01 and also for 0.5. We need to evaluate the frequency overall response of the system, and A naught is 100. So if I want to do this thing, the closed loop gain, is equal to A naught divided by 1 plus K times A naught. For K equal to 0.1, it's going to be 100 divided by 1 plus 0.01 times A naught 100. Okay, so it's going to be, sorry, it's just a mistake here. It's not 0.1, it's 0.1. So it's 0.1. And also let's say K is equal to 0. So let's do for the first one when K is equal to 0. So let me write K is equal to 0. We are analyzing closed loop. So K is equal to 0. So we are going to have something like this. So the closed loop gain will be 100 and my bandwidth will be whatever initially omega naught. So my response will be like this. When K is equal to 0, I am having the gain of 100, okay, which is equal to A naught. And my bandwidth was whatever the previous bandwidth, okay. This is, for example, omega naught. And I'm making this is K is equal to 0. Now, if I K is 0.1, what will happen? Let's K equal to 0.1. This is 0.1 times 100. This is going to be 100 divided by 21. So my gain reduces by 21 times. So this I'm not drawing to the scale, but let me use a different color so that a gain reduces by 21 times. So this is my K is equal to 0.1 point, where it is 100 times, 21 times reduces, but my bandwidth at the same moment increases. So now this is my bandwidth, and bandwidth, let's say K equal to 0.1, enhances by same 21 factor. Same thing, if I use 0.1, 0.5, sorry, my gain will reduce by how much time? 1 plus 0.5 into 100 will be 51 times. Gain will be reduced. So for K equal to 0.5, but my bandwidth will increase. So that's the main message. The overall gain bandwidth product remains constant, but the gain, if increases, the bandwidth reduces, but if it gain reduces, the bandwidth increases. So that's overall cycle which is going to run for all the time. We can apply the same concept to different further stuff, and we can verify the same things that, okay, in our amplification, whenever we increase the gain, the bandwidth will reduce. We will apply this to different amplifiers in future, but at this moment, we will proceed towards another concept regarding the impedance. And that is the last topic which we are going to cover in today's class. So impedance, input and output, both impedance. Okay. For that one, we can simply analyze that, okay, whether the input impedance and output impedance changes because of closed loop, That's what we want to analyze. So that's why let's draw a simple circuit and we can analyze. So it's a common gate configuration. So here we have a in, we have RD. Here we have the out. Okay, so it's a common gate. Input is applied on the source, output is taken at the drain. So we have a common gate system, and we have a feedback. You can see we have a feedback system which is being going here, and at the same time, it's given to us that R1 plus R2 is pretty much bigger than RD. Okay. This is given to us. Let's talk first about the open loop input and output impedance. Open loop, we know that open loop input impedance will be what? Input impedance, we all know, we are seeing from this side, so it's going to be 1 over GM. And output impedance, since R1 and R2 combination is pretty much bigger than RD, so we can write open output impedance is going to be RD. Again, assuming lambda is equal to 0 along with this. So that's what we know that, okay, we can figure it out. And the gain for this evaluation is GM RD. But what about the closed loop? So closed loop, we have to find out using some analysis. So let's find the closed loop one. So closed loop, input impedance find करनी है, so we will apply a test source on the input side. So let's apply a test source. Again, sorry. Test source PDD हो गया यहाँ. So yeah, so here we apply a test source here. We call it VT, and we need to identify now the current which is flowing through here. So input impedance Rin for the closed loop will be VT by IT. So we need to find this impedance. How we can find this impedance? We can simply see, let me draw the small signal, might be more easy for us to analyze using a small signal model. GM VGS. Here we have drain, one terminal is connected to R1. This is the gate terminal, and this is a R2. And this hole is connected to something RD. This is the point V out, just to make sure. And here we are having a test source VT, where IT is going through. So one thing we can write that IT is equal to minus GM VGS. Okay, and VGS kya hai? Is basically minus GM VG minus VT. So okay. And what about VG? VG is ultimately voltage division of this potential, whichever is here. This potential is again multiplied by IT times RD. So it's voltage division IT times RD times R2 divided by R1 plus R2. Make sure you are comfortable with this thing, and minus VT. Okay. So yeah, but IT aa jayega. So if we do the math, we will be IT. So I guess the ink of my is getting discharged my pen, so a little bit. So if we do the same thing, IT will come on this side. Right, so we can divide the GM initially here. So IT divided by IT and GM will come here. Oh no, sorry. IT times RD R2 divided by R1 plus R2 equal to VT. So if we do this plugin, we'll use other color to identify this thing. the VT over IT will become 1 over GM, just taking form 1 plus RD times R2 times R divided by R1 plus R2 times, we can write GM here. So that's something very much interesting. Previously, for the open loop, the input impedance was equal to 1 over GM. But now this is enhanced by the factor, this one. And what is this factor? If you just closely see, this is equal to A naught times K. So this, it's enhanced, the input impedance is enhanced by the factor of loop gain. So because of the closed loop system, the input impedance increases at this moment for this configuration. We are not concluding at this moment, but the input impedance increases by the factor of loop gain. Now, what about the output impedance? Okay, we can do the same thing with an output impedance. We have this system, we have here, we have R1, we have R2, R1, R2, apply a test source here, VT, and we want to find IT here. So VT over IT, if we do the VT over IT, so at this point, what is the potential here? We want to write a potential name Vx. So let me just write this Vx will be equal to R2 divided by R1 plus R2 times VT. And this is basically VGS will be equal to S is 0, so Vx. And the current flowing through is equal to ID, जो इसके अंदर से है, is equal to GM VGS. ठीक है? So if we want to write ID is equal to GM VGS, and what is the relation between IT and ID? We can say that, or not, we can say it's given to us that R1 plus R2 was pretty much bigger than RD. This means that if we just do the small signal model, it will be something like this. GM VGS or ID ये गेट है, R1 R2 RD, and this is IT. So no current will flow because of this assumption from this path. So IT will be equal to ID, which is GM VGS, plus IT will be equal to GM VGS, plus we have the other current flowing through this point, which is an RD. So it's going to be VT divided by RD. Now, if we just plug in the values, we know this point VGS is equal to GM times R2 divided by R1 plus R2 times VT plus VT by RD. And again, if we manipulate, we will come to some conclusion that VT by IT is VT by IT equal to RD divided by 1 plus R2 divided by R1 plus R2 times GMRD. And what is this factor? Again, this is K times A naught. So what happens, our RD is something like this. So same thing, we are concluding that again, in this case, the output impedance reduces by the factor of 1 plus K A naught because of the closed loop factor. Whereas in the input impedance enhances, input impedance goes up by the factor, let's say K A naught, and output impedance goes down by the factor K A naught. And that's pretty much important. We'll utilize in the next lectures. The query or the question still to be asked, is it a generic? We need to see. We have seen this applies to the common gate, but we also have to apply to others before we can identify this analogy. But at this moment, I will leave at this point, but I would like all of you to think over it, whether it's generic, whether it's not generic, and why. So make sure just revise this content. We will build from the same point in the next lecture, and we can just go toward different topologies of feedback systems, and we can also see the current, voltage, voltage, current, voltage, voltage, and current amplification, and then we will apply different types of the feedback system and how we analyze the negative feedback. Right, make sure to send us email or update us if you have any query, concern, and we can also discuss the things in our office hours. Right, so we will just close the session now.